Hello everyone and welcome to Lab Manager's Ask the Expert webinar series. My name is Mary Beth Zidana and I'll be moderating today's discussion, The Basics of Elemental Analysis. We like our webinars to be very interactive, so we encourage you to submit your questions to us at any point during today's webinar. Our speaker will address these questions during the question and answer session following his presentation. To ask a question or leave a comment, simply type your query into the Q&A box located on the right-hand side of your screen. We will try to address as many questions as possible during our time together. If we happen to run out of time, I will forward any unanswered questions to today's speaker and he can respond to you directly if possible. I would like to remind you that this webinar recording will be available on demand shortly following this presentation, so please watch for an email from Lab Manager on how to access this free video once it's available. I would also like to extend a special thank you to our sponsor, EA Consumables, whose support allows Lab Manager to offer these webinars free of charge to our readers. With that, I'd like to introduce our presenter of this webinar. Scott Hughes has a long and storied career in the field of elemental analysis. He founded EA Consumables, the exclusive U.S. dealer for Elemental Microanalysis Limited, in 2013. Prior to that, he founded Elementar Americas and served as president for nearly 15 years. Scott has also been president of Lexay Inc. and vice president of Varlin Instruments. Additionally, he spent 9 years with UIC Inc. as senior vice president. As a known authority in organic elemental analysis, Scott is regularly asked to speak at conferences. Scott holds a BS in chemistry and physics from Beloit College and a PhD in analytical chemistry from Iowa State University, as well as an MBA from the University of Chicago. Scott, thanks for joining us today.
Thank you, Mary Beth. Okay, today we're going to be talking about elemental analysis and its history and current practices. Okay, so these elements are essential: carbon, nitrogen, sulfur, hydrogen, oxygen, to all forms of life that we know. And the big beginnings of chemical theory involve the identification and characterization of these light elements. Today, elemental analysis is used in many, many industries. I've listed a few here, but there are many others. So why elemental analyzers? So people want to measure carbon, nitrogen, sulfur, hydrogen, oxygen, and a wide variety of materials. We can design detectors that sense molecules in the gaseous form. And these tend to be carbon dioxide, nitrogen, sulfur dioxide, hydrogen, and carbon monoxide. But what are we mostly interested in measuring? And we're mostly interested in measuring things we can touch. And what these things have in common is they're not gases. So the question is, how do we get these things into these things? So what to do? So we first go back to basics. And if the first method of conversion of solids into gas were cavemen burning things up. And if we look at the timeline of our way to the current elemental analyzers, so we can start a zillion years ago with the cavemen burning things up. And then we take a big jump to Joseph Priestley in 1774, who discovered oxygen. After that, in 1779, not so far afterwards, we have Antoine Lavoisier. I'm probably pronouncing that incorrectly. So he burned diamonds to make CO2. This picture is probably of his wife prior to him burning her diamonds. I'm sure she was not too happy about all of this. Shortly after that, Justus von Liebig converted by combustion to carbon and hydrogen, different materials. All of these were using coal-fired furnaces, so a pile of coal burning these devices in order to make their conversions. And then in 1833, again, this is a very short number of years, we have Jean-Baptiste Dumas determined a nitrogen method by combustion, also using coal as the form of combustion of the materials. And then we have Mr. Pregel, who puts it all together. And part of this was brought about by, in the late 1800s, the company W.C. Heraeus developed electrically heated furnaces for platinum production. And between 1910 and 1923, Franz Pregel used the Heraeus furnaces and were able to optimize temperature, high temperature combustion in the presence of oxygen and solid oxidants in order to determine carbon, hydrogen, nitrogen using very small sample sizes. And he actually won the Nobel Prize for the first CHN analyzer in 1923 using this technology. And from 1923, not a lot happened except in the world. So World War II kind of disrupted what was prior to that very quick development in this elemental field. And we jump all the way into the 1970s before we have the introduction of today's types of analyzers. So in review, in the early 1800s, they were figuring out that organic materials were made up of largely carbon, hydrogen, nitrogen, and oxygen. And then in the early 1900s, the use of electric furnaces allowed for the optimization and quantization of conversion. And then in the 1960s, we moved to more automated types of detectors of those converted gases. And the 1970s saw the first commercialization of automated CHN analyzers with PerkinElmer's Heraeus, Carla Erba, and they all using thermoconductivity detectors. So this is a picture of these analyzers. This is the PerkinElmer 240 horizontal combustion. This is the Heraeus system, also with a horizontal combustion furnace, and the quite unique Carla Erba, which is out of Italy, using vertical combustion furnaces. If we look at these today, their principles are the same of the early 70s. These are the modern analyzers of Thermo Fisher. These are Elementar. PerkinElmer is still producing one, though it hasn't much changed since the 1980s. And the company LECO has a line of mostly macro analyzers in this field. So we're next going to talk about how these analyzers actually work. And the processes involved are these steps here, which we'll go through in detail during this presentation. And mostly we're going to talk about carbon and nitrogen determination today. Why? Well, it's the most common mode that's used, and it also makes the talk a little less complicated. However, I will intersperse in here some comments about sulfur from now and again, as it does apply. So the first step is preparing the sample for analysis. And the question is often how much sample is required. And the quick answer is as much as is required, but as little as you can get by with. And that's not usually very meaningful for people that are asking the question to begin with. What does that mean? Well, there's some key factors that come into determining sample size. One is the concentration of the analytes to be measured. The other is the availability of the sample. How much do you have? If we're measuring Martian meteors, there may not be a whole lot. You can't get some more. The homogeneity of the sample and the density are all factors. So on the concentration side, let's look at nitrogen. So nitrogen, the working range of these analyzers is between 0.02 milligrams and 1 milligram absolute, though to tell you the truth, the more comfortable working range is more like 1/10 of a milligram to 0.5 of a milligram. And so if we look at our samples here of apples, cows, soil, and pharmaceutical materials, in order to get in that comfortable range, you would need 20 milligrams of an apple, 2.5 milligrams of a cow, 100 milligrams of soil, and 2 milligrams of pure chemical. On the availability side, sometimes you have a lot of sample, as in a big pile of dirt, and then other times the sample, you don't have so much. If you're looking for feathers, there's only so many to have. Homogeneity is another issue. Some materials are particularly inhomogeneous. My favorite here is the raisin bran. If you're trying to sample that, do you get the raisin? Do you get the bran? Feathers can be a challenge too. The tips of the feathers, the bottom of the feathers, the stems can all be different. Other things are quite homogeneous, as in pure chemicals. You can use grinders to help homogenize the samples, but this can also affect the concentration at times. So if you have grinding will create heat, and some of the analyte can be lost prior to getting it into your analyzer itself. So in the case of homogeneity, size does matter at times, because the larger sample size you can take, the more you can overcome its inherent inhomogeneity. Also, the density of the sample can be part of the determination. Getting 10 milligrams or 100 milligrams of a fluffy material in a capsule can be a challenge. Yes, you can choose different size of, in this case, tin capsules to encapsulate the sample, but you also have to be aware that your analyzer will have specific auto sampler size and may not be able to take the larger sample sizes. The next step is combustion of the sample. So combustion, the concept is pretty simple. You take a known amount of sample, enclose it into some sort of a capsule, typically tin. The package is transferred into a tube, quartz or stainless, heated at about 1,000 degrees. You add oxygen, and the goal is to convert the sample into what I'm calling our friends, CO2 and N2. And the key here is to quantitatively convert all of the carbon and nitrogen in your sample into the CO2 and N2, and also eliminate the other interferences that might come along with that combustion. So it's not all that simple because you have limitations. So you have temperature limitations on the combustion. Quartz combustion tubes have a limit of about 1150 degrees Celsius. Stainless steel, which are sometimes used, 960 degrees, but some materials may need a higher temperature to decompose, especially inorganic materials. And you also need to get sufficient oxygen at the correct place and time in order to ensure that you have the combustion. Okay, so I'm showing here two popular combustion tube filling systems. One on the left is the thermo or Carl Urba type of systems. Other manufacturers will also use this basic concept, versus the one on the right is the Elementar type of analyzer. The Elementar introduces oxygen through a lance directed at the middle of the tube. And this is showing the oxygen going down, the sample falling and combusting at the end of the oxygen tube. Where the thermo has a plug of analyzer, a plug of oxygen that is released and times the sample to get down to that point at the same time. The exothermic reaction of the tin and the oxygen together results in temperatures that can get up very localized to 1700 degrees Celsius, so much hotter than the furnace, the tube itself, which is around 1,000 degrees. So the sample is introduced into a tin foil. It's introduced into the furnace at about 1,000 C. Oxygen is added. And we get these formation of what I call this soup of combustion products. And again, our key is to get everything into CO2 and N2 at the end of the whole process. So first of all, this tin exothermic reaction with a high temperature will generally convert your carbonates into CO2. We then go through the chemical parts of the tube, in this case the chromium oxide or the copper oxide in the case of Elementar. We'll get rid of carbon monoxide, forming it into CO2. And then we pass either through silver cobaltic oxide or lead chromate, which actually now today they use silver wool, and this will get rid of chlorides as well as some of the sulfur oxides. The lead chromate really works well getting rid of sulfur. However, it's no longer used due to its toxicity in the lab. But my slides are that old that I still have it in there. So after the combustion, we do reduction reaction. And shown here are the gases from the combustion tube that were left over. Our first step is the nitrogen oxides and the oxygen. The oxygen we added to do the combustion to begin with. So if we put those over copper at about 500 to 600 degrees Celsius, we will convert the NOx to N2, and the copper will grab the oxygen, forming different forms of copper oxide. Now we'll still have some SO2 and SO3 to deal with. And over copper, this will also be absorbed as a copper sulfide, but this would not happen at 850 degrees Celsius, which is important because if we were doing sulfur analysis, we would increase the temperature, which would do the reduction of SO3 to SO2, but also release it for the detector where we could separate it later. Now, the biggest job in the reduction tube is the removal of the excess oxygen, which is shown up here. And we do this over copper. And copper is, as we mentioned before, the copper is a surface reaction, and it is available in different forms. So granular wires tend to have more granular copper, shown here, have higher capacity than wires. The fine sizes are better capacity than coarse, except the fine and granular cause system back pressures and are not necessarily appropriate for all manufacturers of analyzers. And then we have our leftover gases. So we're down to CO2, N2, we're almost there. We still have water to deal with. So now we have to remove the interferences. And our first one is the water. And we can pass this over magnesium perchlorate. However, magnesium perchlorate can form a brick and block flow when it gets very wet. So a trick is to mix in quartz chips with this to stop it. Another very effective material is a product called Secapint, which is phosphorus pentoxide on a support, and it also is an indicating when it's wet. It has great very low vapor pressure, which is good for this application, and great flow properties even when it's wet. However, it is very reactive to water. It can sizzle and cause higher reaction temperatures, and it requires a hood and gloves for filling purposes. So chlorides can be removed with silver or silver compounds. And other halogens, if present, can be removed by adding magnesium oxide to the combustion tube. However, if this will also absorb sulfur, so this is a no-go if you're doing sulfur determination. And there are times when you may want to get rid of this CO2 and only analyze for nitrogen. This is the case with high C-N ratio samples such as tree rings, and there's a huge amount of carbon, very little nitrogen, so we can use a bigger sample size if you can get rid of the carbon. You can pass this over sodium hydroxide on support. Our product name for that is called Emazorb. We'll get more into that later. And after we remove the interferences, now we have separation to deal with. So the analyte gases need to be separated because most detectors, such as the thermal conductivity detector, do not speciate, and we have to add them, send the analyte gases, the N2 and the CO2, one at a time to the detector. And we can do this on a number of different ways. One is using isothermal gas chromatography. So it's just a single temperature GC column will separate the N2 from the SO2. Also used our temperature ramped gas chromatography columns that can control the separation better than the isothermal. And a third type is to use multiple columns that are specific for each of the different analyte gases. And it's sort of a pseudo purge and trap system. So shown here is a trace from an isothermal GC. a little bit complicated because this is actually on a isotope ratio mass spectrometer, so we have a few extra peaks. But what's shown here is you have your N2 peak that comes off first through the isothermal GC. It's separated from the CO2. But then if we were doing sulfur analysis, the sulfur comes out way long and broad, which can cause problems, or if nothing else, just lengthen the time of analysis. If we bring in a ramped temperature GC, you can see that the N2 and CO2 come off as it did over here. It's about the same amount of time. And then with the ramping up of the GC column, the sulfur peak comes out much sooner and narrower. The Elementar system does the same thing, but uses several steps of temperature change. After the nitrogen comes out, it steps up its column temperature here, shown by this line. The CO2 comes off, it increases again. The water will come off as a gas, increases again, and the SO2, where you can get baseline separation of all four analytes. If you're going for larger sample size, then this is where a multiple column system becomes advantageous. Here you have getting a much more dynamic range. So basically, in this sort of situation, you have columns in a row here. Now, this is showing it for all C, H, and S. If you were just doing C and N, you'd only have the one column, or if you're doing S, C, N, you would just have three columns. But the nitrogen first comes through, and it's not held up by any of the columns. It will just go all the way through here and to the detector. And when that has passed, the system then heats up the CO2 column, which then releases the CO2. When that's passed, it heats up the water column, which releases it. A valve changes, which bypasses the CO2 column. And then finally, we heat up the SO2 column, switch a valve, bypass the other two, and you get the baseline separation of all the analytes. Okay, and then we're getting down to the end. Our next is the concentration detection. So going to detectors, our most typical detector for this type of analyzers are thermoconductivity detectors. They're non-selective detectors, so we have to send the gases one at a time to them, separate them first. They're non-destructive, which is really good in case you want to put a second detector afterwards or do isotopic analysis of the gas. They're not particularly sensitive, but they're pretty good with the current technology. Very large dynamic range, they're reasonably linear, and they're robust. Dilution's not possible, but we can alter gain electronically in order to get things on scale. Other detectors that are sometimes used are infrared, which are very sensitive and can speciate as well, typically used for CO gas, which is a form that we'd convert if we're doing oxygen analysis, which is not a part of this talk, or SO2 analysis. Chemiluminescence detectors can be used. They can measure nitrogen in the form of NO at very, very low concentrations. However, they only will respond to nitrogen oxide, and nitrogen cannot be converted to nitrogen oxide quantitatively. It's always in a equilibrium with other nitrogen oxides. So if you keep things steady and calibrated, you can handle that, but it becomes a matrix sensitivity because the ratio could shift with different matrices. UV fluorescence is also used for low-level SO2 analysis at times. And in addition, isotope ratio mass spectrometer is an effective detector unto itself. They're used a lot with elemental analyzers, typically just right after the TCD. So since the TCD is our main one, I want to go through how it works. So first we start with a Wheatstone bridge, which are basically 4 resistors wired in this sort of arrangement here with a power source and a voltmeter across these 2 points. Now, 2 of the resistors are thermistors, and thermistors are resistors where their resistance changes as a function of temperature. So we will direct the flow from the combustion tube across one of the thermistors, and we'll have a second reference flow of our carrier gas that is not from the combustion, but just always clean through the second thermistor. And then we will put it all in an oven at 60 degrees Celsius to keep any ambient temperature from affecting things. And with no sample, but just the helium flow going on both sides, we'll adjust the voltage such that there's 0 voltage across these 2 points. So again, we just have a flow of helium coming through this side, a flow of helium coming through this side. We'll get steady state because the thermistors will have the same flow rate going through. Everything is in balance, and we set things to 0. Now, if the rate of cooling changes on one thermistor, from the combustion tube actually, the bridge will go out of balance and there will be a voltage that we can measure between 1 and 2. And when you have a mixture of helium and some other gas, which is our analyte, it'll have a different heat transfer rate compared to pure helium. So this is showing here the thermal conductivity of helium, 156.7, is vastly different from the different forms of gas that we use for our analyte purposes. In the case that we're looking at here, nitrogen 26, CO2 at 16.8, much different than the helium. So if we graph the bridge voltage versus time, we will trace a peak as a plug of helium and analyte passes the thermistor. So again, we're showing here the flow of analyte and gas, indicating the blue dots as the carrier gas and the green dots as, let's say, N2. So as the N2 starts mixing in, the bridge will come out of balance and we'll measure a voltage. But then as the carrier gas flushes this back through to just pure helium again, it returns to the baseline. And the area under the peak will be proportional to the amount of other gas which passes through. And the system has to be calibrated for each gas type because they will have a different response. Okay, so success. We have taken the things of interest. We put them into the magic boxes of the elemental analyzers. They convert into our analyte gases, and then the computer of the system will hold the calibration curves with the TCD and tell us our percentage of different elements. But a lot of focus is always on the laboratory instruments. That's because these things that cost a lot get a lot of attention, and they're impressive and shiny for laboratory tours. There's big ones, there are tenacious ones, and there's colorful ones. But the simple truth is that if you do not get complete conversion of your analyte to N2, CO2, or in the case of SO2, then the big detectors will not really help you. The instrument is important. As we've gone through, we have to transfer the sample, have a hot environment with a steady carrier gas flow, add oxygen, and the detector does matter for sure. But analyzers and the consumables that they use are like chickens and pigs when they're making breakfast. The analyzer participates in the process, but the consumables are intimately involved in that conversion. So your sample and our products have an intimate relationship since we're a manufacturer of consumables for elemental analyzers. And I just want to go through the different options you have of these consumables for these same points that we've just been talking about. So in sample encapsulation, you have many choices. We have over 400 different types of encapsulation, different materials from tin, silver, nickel, copper, aluminum, cellulose, different forms, capsules, flat bottoms, smooth bottoms, discs, etc., different sizes, weights, and different preparations, whether they're standard or pre-cleaned or ultra-cleaned. Tin is the go-to capsule material. As we mentioned previously, it exothermally reacts with oxygen to help in the thermal decomposition of the sample. It's easy to work with. It doesn't have a zero carbon blank. and the tin oxide is corrosive to quartz at operating temperatures. So there's always compromises with everything you choose. Silver is another one typically used for either oxygen determination, as there's no formation of an oxide, in this case, as it is with tin. It can tarnish when stored, but you can remove it by simple heating. It has no exothermic reaction, and it doesn't form ash. It actually forms a silver melt in the reaction tube. And it's stiffer and not easy to work with compared with tin. It also costs more, but you can have big savings if you use lightweight silver capsules. But a hint is to collect the waste, because you can collect it over a period of some years and sell it back to get a refund from recyclers. And with that, you can get enough money to have a wild laboratory party. Other options, cellulose capsules are used in nitrogen-only analysis. They have low ash, higher blanks due to the open tank, however. And you can get these in all different forms of pressed capsules, squares, discs, evaporating cups, and things of this nature. Another thing is the combustion aids. Combustion aids are used to help in the combustion tube itself convert, or is added to, in this case, I'm talking about combustion aids that we add to the sample itself for the combustion. In the case of low carbon nitrates, they need help. Fertilizer samples are a typical one. The carbon actually helps in the combustion and conversion of the nitrates to the nitrogen oxides. So for these samples, sometimes you'll add sugar, carbon powder, or benzoic acid to the sample. Sulfur determinations are often used with a combustion aid. They block undesirable side reactions such as stable sulfides and carbonates, and it will also fuse the alkali and alkaline earth oxides to stop those formations. Vanadium pentoxide is a typical one, but it's toxic. Tungstic oxide is another option. Other ones, most of these just add oxygen to the sample. Most samples don't need this, but some tough ones do. Magnesium oxide, we mentioned this before for binding fluoride, but not when you're measuring sulfur. And tin powder is sometimes added to the sample to create that extra exothermic reaction in addition to the sample encapsulation to form more heat to combust the sample. Then we have the oxidation reagents inside the combustion tube itself. Depending on the form of analysis and your manufacturer type, different combustion reagents will be used. In the case of CN, CHN, or CHNS analysis, either chromium oxide, cobaltic oxide used, copper oxide, tungstic oxide. In the case of sulfur or protein, some analyzers don't use any here. But then in the case of protein or macro analyzers, a second combustion tube is used called post-combustion, in which some manufacturers will add a platinized catalyst or graphite into the sample itself. So many different options are available. Interference removal and absorption materials. In the case of interference removal, we're often talking about sulfur or halogens. We've talked about some of these before, the silver wool or silver reagents can be used. In the case of halogens, there's a whole number of things, and some are just oxidative help. So we have many different options available within our product line. And for absorption material, we're talking about water. Magnesium perchlorate is very commonly used. It's available in regular forms as well as indicating. We also have it in 25-gram quantities, which is a great help financially because it can ship under an accepted quantity shipping and doesn't incur extra surcharges. It does get wet and hard, which has caused blockages. The secapent is the other option, also can be in 25-gram sizes and has good flow properties when wet. Absorption materials. In case you're doing nitrogen-only analysis and you want to get rid of the carbon dioxide using sodium hydroxide on support, our product name is Emazorb. It turns black to gray when it gets when it absorbs the CO2. Soda lime can also be used in this application. These are hazmats and also come in 25-gram bottles for being shipped without the surcharges. Other things of absorbing water or liquid type samples, you can use Chromazorb W. It's like a diatomaceous earth. It's mostly SiO2, so it will not add to nitrogen or carbon. And it's used for a liquid absorbent for liquid samples. Next is reduction agents. Mostly we're talking about copper. Went through this before. The copper is available in many different forms. Some are advantageous for different types of analyses. Tungsten is used in the Elementar systems for certain protein analyzers and their macro analyzer. And the Elementar also has a copper oxide reduction tube in the case of the Elementar Exceed type of analyzer, but that's a topic for another talk, another day. And finally, certified standards. We mentioned before that the TCD detectors do have to be calibrated, so you need standard materials of known composition to do that. And we have high standards and low standards, and we even have some double standards, but the bottom line is we have a lot of different standards, and they're all certified, over 300 different types, and all come with a sort of certificate of analysis traced back to NIST. So in conclusion, for successful CHNOS determinations, you have to get complete conversion of the sample into the analyte gases, removal of interfering substances. Reagents can be tailored for specific types of samples, and preparation of the reagents has a significant effect on the effectiveness and life of the reagents. And so in conclusion, chickens and pigs can get along well together. Let's just skip breakfast. Okay, so that is the presentation, and I welcome any questions you may have. So we can.
All right, great. Thanks, Scott, for that wonderful presentation. So at this point, we're going to move on to the Q&A session of this webinar. Again, for those of you who may have joined us late, you can send in your questions by typing them into the Q&A box on the right-hand side of your screen. Even if you don't have a question, we invite you to leave a comment. Let us know how you enjoy this presentation. And if you leave a comment, we will have a record of your name and contact information, so Scott and the EA Consumables team can get back to you if you would like. So Scott, thanks again. Let's get into the first question here. This one says, how do you analyze for only organic carbon using an EA?
Okay, that's a common method. A lot of soil people are only interested in the organic carbon. And the most common method, there's a few ways you can do this, but the common method is to remove the inorganic carbon by adding acid to the sample and then analyzing the remaining material on the EA. So what you have to do is weigh a sample, and you have to weigh it onto a silver boat or capsule because we're going to be adding acid, and if you use tin, the acid would dissolve the tin. So then you add typically concentrated hydrochloric acid dropwise onto the sample, and you may see some sizzling if there's any carbonates there as the carbonate turns to CO2, which is a gas. And then you add it dropwise until it stops sizzling. Then you put this on a hot plate and you heat it in the open silver container to dry it out. And then you are ready to analyze it, but you have to fold up the silver capsule. But by this time, there's a lot of acid residue on the outside of the foil. Tin also gets kind of brittle even with the acid, etc. So typically you will take that silver foil that's been acidified and heated, put it into a tin capsule, and then fold that all up, put it in the analyzer for analysis, and you'll be measuring just the organic carbon. Now, the residual chlorides from this digestion will result in shorter consumable life, so be aware of that. Instead of adding the acid dropwise, some folks would prefer to use a HCl fumigation method. In any case, whatever method you're using, you should avoid using sulfuric acid, as the sulfur load is pretty problematic for elemental analyzers.
All right, wonderful. Thanks so much. Let's move on to the next question. This one says, what are the causes of getting lower results than reasonable?
Okay, most usually low results are caused by a leaking analyzer. For almost any problem with the elemental analyzer, it's always advisable to do a leak check as a first step in troubleshooting, because leaks can manifest themselves as lower results, sometimes even higher results, though not typical, and long analysis times. It's always good to get that off the table first. Other reasons are usually sample specific. High nitrates, for example, with very low carbon, are difficult to quantitatively convert all the nitrogen to N2, which is the form we have to measure it in. And if you're only interested in nitrogen determination for that type of sample, adding a carbon source such as sugar or benzoic acid greatly helps convert things. So there may be other reasons with other different types of samples, but that gets into, but those are typical ones that I just mentioned.
Okay, great, thank you. Here's another question here that says, how do you analyze liquid samples?
Okay, a couple methods here also. One is, especially if you have liquid samples which are volatile organics, the typical thing is to use a smooth wall tin capsule and a special sealing press, which is designed to purge the head space of the capsule with oxygen and eliminate the atmospheric nitrogen that would be on top prior to cold welding them shut. Of course, EA Consumables does supply a special liquid sealing press for this purpose, as well as the tin capsules. Alternatively, if the liquid is not volatile, you can use a liquid absorbent such as Chromasorb W. This would be appropriate, again, for only non-volatile liquids. And the way you do this is you take your tin foil, you add some Chromasorb to the tin, and then you tear that on the balance, so you get the tin and the Chromasorb is weighing 0. Then you add your sample to the appropriate weight, and the Chromasorb will absorb the liquid because it's a diatomaceous earth type of product. No carbon is in it, so it won't cause problems to your analysis. And then you seal it and place it into the auto sampler. There are how-to videos on the EA Consumables website shown here on the screen, the www.eaconsumables.com. And under the how-to video sections, there are different videos for both those preps that I just mentioned.
Okay, great, thanks. We actually have a follow-up question that came in. It says, can you please define volatile organics? What would a volatile organic or liquid be?
Volatile organic would be a material that would turn into a gas at near or at room temperature. So things like acetone or ether and things of that nature would be a volatile organic.
Okay, perfect. Thank you.
Okay.
This next question says, how do you analyze liquid samples?
No, that's one we just did.
Oh, sorry about that. Okay, I'll go to the next one. Okay, this next one says, how can I be sure that I provided enough of a sample to measure? How will I know if I have too much or not enough?
Okay, the way to determine this is to look at the peak graphics from the analyzer, and that will be telling you the story. The absolute amount of sample or analyte that can be handled will be a function of your analyzer itself, as well as the mode of operation you're in. So check with the operation manual for guidelines on that. It will be different from instrument type to instrument type. But in general, too small a sample will result in analyte peaks, which are very small and have significant variation. Too much sample can result in either incomplete combustion or incomplete separation of the different elements. For example, If you have, if the nitrogen peak does not have baseline resolution from the CO2 peak, typically that could be way too much sample. Tailing of the peak is also a sign of incomplete combustion or too little oxygen for the analysis.
Okay, wonderful, thanks. We have another question here that says, are there any specific types of samples that cannot be handled?
Yeah, our range of samples that we can handle are things that can be combusted at temperatures around 1,000 degrees Celsius. For this technique. So what's not combustible around there? Well, metals and alloys are not appropriate. These require much higher temperatures, and there are specific inorganic analyzers with induction furnaces for these types of determinations that go up to these higher temperatures. EA Consumables does supply consumables for these types of analyzers as well, but that would be the topic of another webinar.
Okay, wonderful, thanks. We have time for a couple more questions here. This one says, is it possible for a sample to be corrupted? How will I know?
Well, samples can be corrupted, and it all depends on the type of sample and so forth. I mean, in certain cases, if material is hygroscopic and you leave it open to the atmosphere, it may be absorbing water, and that will affect the percent carbon, nitrogen, hydrogen as a function of when it was originally sealed before the water went in there. Obviously, other contaminants, if someone dumped some standard in it or whatever, mistakes can happen. It's really tough though to tell it instrumentally. I mean, the only way to tell it's corrupted is if you know what the sample should be or the range, and it's way out of range. Maybe it could be a corruption problem, but the analyzer won't have any smoking gun that will actually tell that, because it basically will just measure whatever you give it.
Okay, great, thanks. This next question says, how will I know if my instrumentation needs maintenance or servicing?
Sometimes it's very obvious. For example, when the reduction reagent is used up, so all of the added oxygen for the combustion will not get scrubbed out of the system, and it will go to the detector and look like nitrogen, and your nitrogen peak will be humongous. So that's like real obvious. All of a sudden you have a 5% nitrogen, and the next sample you have 2,000% nitrogen or something like that. When other reagents need to be changed, it can be more subtle in the combustion tube, for example. And usually you're counting how many samples you've run before you've changed it, so you have some idea that you're coming up to a change time based on the manufacturer's recommendation for the analyzer. But otherwise, you're looking at the standard deviation of results. And as the standard deviation starts getting bigger, you can kind of think of that maybe reagents would need to be changed.
Okay, great, thanks. We have time for one last question, and this one says, what if my sample is of unknown origin?
Okay, unknown origin. So, and you have no concept probably of what the approximate concentrations are. It's always good to take some of the sample, if you have enough of it at least, and start with a small sample size and analyze it. Maybe not to try to get good results, but just to get a range. So then you can adjust the sample size based on that pretest. So if it's some sort of organic material and you put in 1 to 5 milligrams or something like that, then you get an idea of the percent of each element, and then you can adjust the sample size accordingly.
Okay, we actually have time for one more question here. Where can I go for more information or resources?
Just reach out to our team at EA Consumables for any additional questions. Contact information is on the screen right in front of you.
Okay, great. Thanks so much.
You're very welcome.
This brings us to the end of this webinar. Just a reminder that this webinar will be available on demand shortly following this presentation. Please watch your email for a message from Lab Manager once this free video is available. On behalf of Lab Manager, I'd like to thank Scott Hughes for all of the hard work he put into his presentation, and I'd like to thank all of you for taking time out of your busy schedules to join us today. Once again, thank you to our sponsor, EA Consumables. Their support allows us to offer these webinars free of charge to our readers. For more information on all of our upcoming or on-demand webinars, or to learn more about the latest tools and technologies for the laboratory, please visit our website at labmanager.com. We hope you can join us again. Thank you and have a great day.